All right. There seems to be a lot of questions on number 8, which I expected. The problem was that people were asking me the questions 30 minutes before the assignment was due. So there's not a lot I can do for you when it's 30 minutes till and you're running into issues, right? So what I'm going to do is this. I want everyone to turn in what they have, and then I'm going to offer, you can go home after I talk about number 8, you can go home and redo it and turn it in next class, all right? But I want to know what you have now. Yes?
Are you recording?
Yes? Why?
No, I just wanted to go back and doing it.
Oh yeah, I'm recording. All right, so I will collect what you have, please. Pass those up. Were all the other ones okay? No? Which other ones cause problems? 7. What was 7? Oh, the right cylinder.
The volume.
Volume one? Okay. I think you turn out on that one, I believe it's something like the radius is, I don't know, something root 3. I don't know. I'll have to go back and look. 3 root 3 and 6 root 3?
Yeah.
Something like that.
3 root 6.
Yeah, something like that. Okay. I'm going to talk briefly about this because we really don't have a lot of time for this. If you would have asked me how to do this problem a day or two ahead of time, I would have reminded you that, well, you're trying to find, I would assume that you could at least get the objective function and the constraint. The objective function would have been the distance function, right, which would have been the square root of x squared plus y squared plus z squared. So I'm assuming you at least got that much of it. And then there are 2 constraints, right? Constraint 1 is this one, move everything to one side. The second constraint is this one, right? Okay, so the problem that people were having was that you're going to have lambda and mu, and it was really that derivative, it was the partial of f that sucked because it had the root in it, right? And that root screws everything up. It just makes it a lot harder than it has to be. So I'm going to show you something that you may have seen in Cal 1, but it's been a long time. So I'm just going to show it to you now, put it into your memory bank. Don't ever forget it because it'll be something that'll become useful if you ever have to find a max and min of a function involving the square root ever again. And that's this simple fact. If we call this right here d, right, for distance, right? That's what it was. We are trying to find the minimum and the maximum of d, right? That's what we're trying to figure out, the x, the y, and the z that will give you a minimum and maximum of that distance function constrained to those 2 curves. This is equivalent to finding the min and max of d squared. In other words, the highest and lowest points of this function are also the highest and lowest points of this function, which means that you can square it to start the problem. All right? And that makes your life easier because what you do is you say, okay, instead of looking at f, I'm going to look at f squared, which is that. And then your partials are so much easier to work with. And then you go back and you'll get an x, y, and a z. That x, y, and z give you the max and min of d squared. But I'm telling you that those values will also correspond to the max and min of d. So it really just comes down to something like this. If this function right here, f, by itself with the square root, if that is a positive function, which it is, right? It's above the x-axis, or it could touch. if you have a function that is always above the x-axis or possibly touching, I'll just do this. Okay? If that's your f function, which I call d, if I square it, it's going to be a new picture, isn't it? All the x-intercepts are still in the same place though, right? Because when you square 0, it's the same thing. All these values right here get squared are still going to correspond to highest and lowest values. All right? That's the key to that problem. Now, it can be done without that, but the problem is much easier this way. So I recommend, if you want, you don't have to, go back and do that problem, do d squared. Just remember though, oh, it doesn't ask you for the actual distance, does it? So just find the points. So the x, y, and z that you find will be your closest and furthest. But when you go back to actually compute the distance, if you really wanted to know how far, you would have to go back to this one, not to d squared. All right. How many of you had seen that before? D squared? Okay, that can save your ass in a lot of situations where you're trying to find the maximum of a function. Okay. I have another exam. They just keep coming. But this one's not due till April 6th. Take one, pass. All right, there's only three. Whoa, what happened to this one? Stapler missed this one. Now it has 4 problems. Yeah, these will just pass these back, and that has 4 problems on it. They're coming. One more? Here. This one's not stapled. All right, we can talk more about that later. I think you could probably handle the first one, maybe the second one. I did provide these online also in CDF format, so if you want to rotate things around and take a look at what you're working with there, and also in PDF format if you need to print it out. Now, little warning, I did post them earlier today. I realized there was a typo. I just updated it. So if you downloaded it earlier today, go back and get it because I just fixed it about an hour ago. All right? All right, last time, do you remember what we were doing? Double integrals over rectangles, right? Now the homework for 12.1, I did the problems, selected problems, and I put that on YouTube. I also did the homework for 12.2 today, so that's on YouTube. You can watch that later if you're doing your homework. All right, so we're going to go now and get a little more general about our regions. We're not going to restrict ourselves to rectangles anymore. So that's what we did last class, right? We had a rectangle. We were integrating over this rectangle. So, you know, the ground, that was the ground, right? The surface was above it. We were looking at the volume straight down. I told you there were going to be 2 types of regions we were going to look at today, type 1 and type 2. A type 1 region is any region D, we're going to use D instead of R. R is like rectangle. D is just going to be like domain, I guess. Our region D is the set of all ordered pairs, that's the points in 2-dimensional space, such that your x is between two constants, so that's just like the rectangle, right? But this time your y value is stuck between two functions of x, right? So it used to be with the rectangle that your y was stuck between two constants. Now your y can move around. So there's a picture of a type 1 region. Notice that this is very much like an area problem from Cal 2, isn't it? Like where you have your first limit of integration, your second limit of integration, then you were doing like this function minus this function. Remember that? I'm doing that in Cal 2 right now. That's why I'm saying, like, I know you do see that in Cal 2. That type 1 region is kind of a classic area problem from Cal 2. That's our region of integration. That's what we're integrating over. So when we draw our regions, it might be good for us to kind of draw like an arrow, like a line or something, that shows that the lowest value of y, right? This is the y direction. So the lowest value of y is determined by some function, right? G sub 1 of x. The highest value, right, is controlled by some other function of x. And then our x values just vary back and forth. So if I move x between a and b, it moves this line over. And again, it's the same function on top, same function on bottom the whole time. Yes? Any region that looks like that is called a type 1 region. And to integrate a type 1 region, we're going to do a double integral over the region D of the function f of xy with respect to what? Area, right? With respect to area. And this is the actual integral. So what's the big difference between this and what we did last time? There's functions as limits of integration, right? Instead of c and d, we have two functions. And because of that, you are not allowed to change the order of integration. You are stuck. If you're going to do a type 1 region, your constants, a and b, have to be the outside integral. And then the inside integral has to contain the functions. So your order of integration is fixed. If we have two surfaces, right? So now we have some surface f and then some surface below it g, and we want to know the volume between them. We said last time you just subtract the two, right? But that was over a rectangle. Here we can do the same exact problem but over, can you all see that that's a type 1 region? Can you all tell that's a type 1 region? Okay, you've got your restriction on x, and then your y is in this direction, so there's your lower function, g sub 1 of x, g sub 2 of x. So it'll be the same thing that we did last class, the same formula, but again, did I have it there? Yeah. Okay, so it's just reiterating that you subtract the two double integrals, or put them together and subtract inside. Best way to do a problem, get a feel for this, is just to work one out. Find the volume under z equals x plus 2y. What is that if I graphed it? It's a plane. Find the volume under this plane on the region bounded by these two curves. All right, so let's talk about this region. I'm going to try and draw it first. Remember, this is my domain over here, right? This is what I'm going to integrate over. My guess is that this is going to be a type 1 region. Wouldn't you say? Okay, makes sense that it would be, right? All right, so let's graph y equals 2x squared. That's a parabola, right? Starts out at the origin. I'm going to do this. I'm going to use my colors today. So this is y equals 2x squared. And then 1 plus x squared is another parabola, right? Which opens up also, but it's moved up 1. It's also wider than this one is because 2x squared stretches you out or compresses horizontally or stretches vertically. So when I come here to 1, my parabola should go out like this and be wider. That is my region of integration. We okay with this? Yep. So that is y is x squared plus 1. Everybody comfortable with seeing the region that's bounded by both of those? So all of this stuff in here, that's D. So the question now to you is this a type 1 region? Well, it's not a rectangle, right? So we can't do what we did last class. So if you think it's a type 1 region, then you need to be able to draw a line or a little arrow in here like this vertically, and imagine moving this back and forth through your entire region D, and your top function should never change and your bottom function should never change. It should always be the same two. So is it, if I move that around, is the one that's red always on top? Yeah. Is the one that's blue always on bottom? Yes. So you see you have an upper and a lower function there? So the upper function is my g sub 2 of x. The lower function is what we call the g sub 1 of x. Does that make sense? Yes.
So, in the order of integration, which one would go on top?
2's on top, 1's on bottom. So the upper limit is going to coincide with the upper function. The lower limit of integration is the lower function. So it's good. It works that way, right? So I'm just going to write here, this one is x squared plus 1, and then this one is 2x squared. That all right? What's the other thing we need to resolve? Where they hit each other, right? Because where they hit each other is where I'm going to determine, or what's going to help me determine where I need to cut my x's off, right? X is going to have to be between here and here, right? That's the question. What's this A? What's this B? What are they? So you have to find the intersection points. So to find the intersection, you set the two functions equal to each other. Plus or minus 1. Subtract x squared to both sides, square root, plus or minus. So we know that this is A is 1, and, or sorry, A is negative 1, and B is positive 1. And at that point, you set up the integral. All ready? The double integral over the region D of the function of x and y with respect to its area will be equal to the double integral d, you tell me here. So dy, dx, dx, dy, which? dy, dx. Now the way you remember that is the outside integral has to have the constants, right? So the outside one is going to be negative 1 to 1, right? The next one, the inner one, is the restrictions on y. So the y restrictions were these two. So 2x squared on the bottom and x squared plus 1 on the top. And then the actual function that we're integrating is what? This right here, right? That's the surface above that we're trying to find the volume underneath. So x plus 2y. That's it right there. This is our type 1 region. Questions? Comments? Concerns? Integration time, right? So when I go to integrate this, I'm going to leave the outer integral alone. I like to put a set of brackets. Let's find the antiderivative of this with respect to y. So what do we have? xy plus what? Y squared. And we're evaluating that. Now this is where things get a little weird. Y is the variable, right? So we're going to let y be first the lower limit of integration, which was 2x squared. And then we're going to let the upper limit of integration be x squared plus 1. We're going to figure all that out, and then we're going to finish out the outer integral. So this is the first time we've ever done this, right? We've never before had to plug in a function into our antiderivative. So this will be equal to -1 to 1 integral, and then bracket. I will have two things when I'm done that I have to subtract. Figure out what that is, dx. So let's plug in to this expression for y, x squared plus 1. Okay? So x times x squared plus 1, I'll just put that here, x times x squared plus 1. And then plus y squared, so plus x squared plus 1 squared. Everyone see that? Then redo this again, but this time replace y with 2x squared. So x times 2x squared plus, what's y squared going to be? Square this. 4x to the 4th. I'm going to clean this all up first before I integrate it. Integral -1 to 1. I'll just do a parenthesis now. I'm going to have distribute through x cubed plus x. Can we square this? Plus 1. That's squaring that. Okay, this right here is 2x cubed, but I'm subtracting it. And this is 4x to the 4th, but I'm subtracting it. That. Do we have any like terms? We do have some, right? Questions? All right, let's put them in descending order. X to the 4th, we have -3. X to the 4th. Took care of those. X cubes, -1, so -x cubed. Got those. X squareds, only one of them, right? Then plus x plus 1. All right, so I've got everything taken care of there. And that's trivial at this point? Is that trivial? Yes? ... So I'm not going to finish it. You know what to do now, right? All right. Okay, let's take a look visually at what we just did. You sure there aren't any questions? Comfortable with the antiderivative of that? I know my Cal 2 students would tell me, please give us like 100 of those on a test and we'd be happy, right? Just give us a bunch of those. So I'm assuming here you're happy to see that at that point. But you probably feel unsatisfied because I didn't give you like a nice numerical answer. There's the domain in two-dimensional space. There's that same domain laying on the ground in three-dimensional space. Here's the surface, which we said was a plane. Here's just the region there plugged in where it would hit the plane if you map those points up into the function. And that generates a solid if you look straight down. Let me pull all this junk out of here. It's kind of jaggedy. That's just because I have the computer not plotting a bunch of points. Damn it. There. We found the volume of that solid. Well, we didn't. We almost did. Okay? Whatever numerical answer you would have gotten for that represents the volume of that solid. All right, cool. Is this different? Yeah. But those aren't the same two curves. Okay. So let's just look at this one. So your function that you're going to integrate is x squared plus y squared, right? That's going to be your integrand. And now you want to look at the region bounded by these two curves. See, right now you know these are going to be type 1 because that's all we've talked about. But when you get to your homework in problems like 21 through 29, they don't tell you what type region it is. So you're going to have to determine that. And until I show you type 2, you still kind of don't know what I'm talking about. So just keep that in mind when I'm approaching this. I'm always looking at this as I don't know what type region that is until I draw it. So x squared, that's familiar. (2x). It's a linear function. Something like that. We all see the region? It's that little sliver, right? How do I know that 2x is above x squared? Yeah, I know, but I'm saying when I drew it, I put the red one up there. Like, why? How do I know the red one doesn't come out over here? Like, you could plot a couple of points just to verify. All right, that region is a little too small. I'm going to kind of make it bigger over here. I'm going to exaggerate it. My parabola is doing like this. And my line is doing something like this. And if I think that this region is going to be type 1, then I'm going to need to be able to draw a vertical double arrow like this and move it left and right and make sure that the red one is always the top and the blue one's always the bottom. And is that going to be the case? Yes? Okay, so what's the top function written as a function of x? G sub 2, right? And 2x. And then G sub 1 is the one on the bottom. And that's your x squared. What still remains to be found? The intersection, right? Now this one I think we can all agree we don't need to go find, right? 0? But we do need this one. So to find that, you set x squared equal to 2x, right? And what's your solutions? You get two of them, 0 and 2. 0 and 2. I'm not showing that, but that's what you would get. So this is 2. So as I slide this thing left and right, the x's are stuck between 0 and 2. The y's are stuck between two functions of x. It's type 1. We set up the integral, go to town. Yeah? All right, for this one, I'm just going to set the integral up. I don't think I'm actually going to do any of it. Unless you want me to. I'll take a vote. What's the bottom limit of integration here? It's g1, so x squared, and then 2x. And you can even put y equals if you want. Y equals x squared, y equals 2x, but I usually don't. The book doesn't either. What are we integrating? Yeah, that's our order. X squared plus y squared, and then dy dx. Okay? That's it. Integrate this with respect to y. Let's just talk about it. It would be x squared y, 1/3 y cubed. You'd go in, you'd replace y with those two things, figure that out algebraically, and then go back through, integrate that, plug in your x's, and be done. So dot, dot, dot.
Let's get on a test.
What's that?
Let's get on a test. Dot, dot, dot.
Dot, dot. Yeah, on the test, you just put dot, dot, dot. Yeah. All right, so then what is a type 2 region? A type 2 region helps you deal with regions that you have when the curves you're looking at are not functions of x. So this time, what we're going to have is we're going to have that our y value is trapped between two constants, and our x values are stuck between two functions of y. So it's basically a sideways picture of what we just did. You have your y's are stuck between two places. If you draw a horizontal double arrow, then your left x, right, your left x value is bounded by the red curve. Your right x value is bounded by the blue curve. And so the blue and the red functions are both functions of y. So we'll call this one h sub 1 of y and call this one h sub 2 of y. We just use h instead of g. And so what do you think the integral is going to be? Double integral. What do you think what's the order of integration going to have to be? It's going to be dx dy this time. You're going to have on the outside one the y's. So we use c and d so we don't confuse them with a and b. And then here it's going to be our, which one do you think happens first? H1. H1 and H2. So with G1 and G2, it was easy because you could say, G2 on top, G1 on the bottom. This one, it's H2 is the right one, H1 is the left one. Or if you turn your head sideways, it's the same thing as a type 1. Understand? All right, and then in here is the f of xy. Now, there's something in this problem that kind of gives it away that this is going to be a type 2. What kind of gives it away?
Y squared.
That y squared. You see it in there? You see this right here? Y squared is equal to 2x plus 6. If you try and turn, well, let me go back. This right here you could say is a function of x, right? Y equals some function of x. Y is x minus 1. This one, though, to turn it into a function of x, you'd have to solve for y, which means you'd need a plus or minus, right, when you take square root. And so you're actually going to have two functions there, and that's the problem. It would be easier to solve this for x, wouldn't it? And then this one would also be easy to solve for x. Okay. Let's see if we can draw this, though. Y equals x minus 1. That should be easy for all of us to draw, right? Y-intercept of -1 has a slope of 1. Looks like this. But how about this one? How are you going to draw this? It's a parabola, right? Sideways. So let's see how we could do that. Let's go ahead and try and solve this. Let's solve that for x. We get y squared minus 6 equals 2x, right? If we divide both sides by 2, we get 1/2 y squared minus 3 equals x, not 0. And just rewriting it in a different order. Now, in the back of your mind, you could do this. Just think about, what if it were switched? What if this were y and that were x? Then would you be comfortable graphing this? What is that? X squared parabola. Half parabola makes it wider, right? And then moving it what? Down 3? So this is the same idea except sideways. And so it's a parabola that opens up sideways, right? But it's wider, and it's, what's down 3 mean for us sideways? It means to left 3, right? So remember, positive is that direction, so negative is this direction. Just like here, positive was up and negative was down. So it's the same idea, just this way. And then we draw it. -3 is over here. And I don't know. They're going to hit, right, somewhere. Y'all good? Type 1? Type 1? Type 2. So let's look. If I try type 1, if I draw a double arrow right here, right, the blue function is on top of the red function, and that works. But as I move that over to the left, what happens eventually? How about when I get over here? Blue on top, blue on bottom. Same function. That's a problem. And that's why you can't do it as a type 1. Because this curve is the same as this curve, right? So technically, when I try and do the top curve minus the bottom curve, over here, I'm going to get 0. Something's going to go wrong there because it's the same function, same curve. So type 1 is no go. But if we do type 2, we draw these little arrows sideways, horizontally, then move that up and down through here. No matter how you do it, the blue one will always be the left bound. The right one will always be, the red one will always be the right bound, won't it? No matter what. So better suited for type 2. For sure. And because it's type 2, what I need to do is rewrite these curves as functions of y instead of x. So can you tell me what this blue curve is as a function of y? We got it and solved it for x, didn't we? That creates the function of y right there. This left side gets replaced with, what letter are we using? H. H sub what? 1 or 2? 2, 1. The one on the left is 1, right? Okay. So h sub 1 of y is what? 1/2 y squared minus 3. Yeah? Then this red one, which is our right bound, is our h sub 2 of y. And that is the line solved for x, which we hadn't done, had we? We hadn't solved this for x, but we could. Y plus 1. Y plus 1. Right? So take this, That's x equals y plus 1. That's how I got to this. That's an arrow. No questions? What else is still out here for me to resolve? Bounds on y. So we want to know where these hit each other still, right? But we want to know that point and that point, because this is going to be our D, and this point down here is going to be our C. So you see, it's everything just sideways. Same picture, just turned, rotated, basically. So how do we figure out where these two hit each other? Set them equal to each other, right? Set the functions equal to each other. In other words, set this equal to this, right? That will give us our intersection. So I'm going to set 1/2 y squared minus 3 equal to y plus 1. Notice that the equation that I'm using here has y's in it, so my answers are going to be y values, which is what I want because my type 2 region should have constants for y's. This is a quadratic equation, so if I were going to solve that, I would just clear out the fractions first, multiply everything by 2. And then I get everything to one side. What, minus 8? And then I'd hope it factors. And if it didn't, I'd use a quadratic formula. But it should factor. Minus 4 plus 2 are the factors. Y minus 4, y plus 2. Two solutions, 4 and negative 2. That's reassuring because I should have two y values where they hit each other over there. So, feeling good. C is going to be the one below, so negative 2, and D is going to be 4. Now let's just write the integral. That's all it is now. All right, here we go. Double integral. What are the limits on the first integral? Negative 2 to 4. And then second integral, what's the limits? 1/2 y squared minus 3 up to y plus 1. The integrand, xy d x dy. There we go. Would you like me to work this one, or do you want me to just say dot, dot, dot? Dot, dot, dot? Okay. On the homework videos that I did for this section, I worked through the first couple, so you can see all the little details of plugging in and. Okay. What do you all think? I'm not quite sure how to gauge what I'm getting from you all right now. Are y'all tired? Y'all ready for summer or what? Remember, we're like halfway through the semester. It's not like Christmas break, or it's not like Thanksgiving where you come back from Thanksgiving, there's like a week or two of school and then it's all over. No, we still got a long way to go. So deep breaths. There was the region. I'll do this one quickly. It's kind of an interesting solid. There it is. Find the volume of the tetrahedron bounded by this. this, this, and this. All right, so what's a tetrahedron? What's tetra? 4? A pyramid is an example of a tetrahedron, kind of.
You gave us tetrahedron on the first.
I did give you a tetrahedron on the first exam. Exactly. Yeah, so look, the reason I didn't say pyramid was because I think the standard pyramid that we think of,
It's 4 for the base.
yeah, has like, you know, one top and then 4 corners on the base. Tetrahedron, we're going to have 4-sided. It's going to be 4 surfaces, four faces. This would have 5, wouldn't it? Okay. So I have a tetrahedron that is created by, that is formed or bounded by this, which if we graph this, this is a what? A plane in 3-dimensional space. What is this? A line in 2-dimensional space, but in 3-dimensional space, it's a what? It's a plane. X equals 0, what's that geometrically? A line in 2-dimensional space and the YZ plane in 3-dimensional space. Remember one of our first conversations we had, like, what does X equals 0 look like in R1? What does it look like in R2? What does it look like in R3? Okay, so understand what the question is asking here is, you have 1 plane, 2 planes, 3 planes, 4 planes in 3-dimensional space. They enclose some solid. What's its volume? Now, if we want to say we're only looking in 2-dimensional space, I agree, that is a line, and, well, Z, hold on, we're in 2D, so Z wouldn't count, would it? So how in the hell are we going to draw this? So let's agree with something here. Let's try and draw this. I don't think we've ever tried to draw a plane the way I'm about to do it. Let me just try and draw. There's my X, my Y, my Z. All right, let me try and find if this plane hits the x-axis. Does this plane hit the x-axis? If so, where? So if you're on the x-axis, what's your y-coordinate? What's your z-coordinate? So if y and z are both 0, what's x? 2. So do you agree I would be out here 2? That point lives on the plane? Agreed? What about the y-axis? Does it hit the y-axis? At y is 1. So this time, if you're on the y-axis, x is 0 and z is 0. So you would get just 2y equals 2, so y would be 1. That point lives on the plane. And what about the z-axis? Where does it hit the z-axis? Up at 2? So what I can tell you right now is that this plane passes through all 3 of those points. So if I connect them with lines, that triangle lives on that plane, doesn't it? But it still extends in every direction forever. All right. What does x equals 0 look like? If I graphed it? That's the YZ plane. Isn't that this wall right here? So it's the entire wall, isn't it? Doesn't that kind of like close off the back section of this tetrahedron we're creating? You all see that? That's like a back wall of that tetrahedron. What does z equals 0 create? XY plane, which is the floor, isn't it? So everything down here. And then, one more thing. There's one more plane that we need to look at. X equals 2y. So what, that looks like a plane, right? Could I draw it on here? Can you draw me the plane x equals 2y? Can you tell me one point for sure that it goes through? The origin, right? 0, 0, 0, 0, 0 lives on that plane, doesn't it? If x and y are both 0. So let's see what color I've got left here. I know this point lives on the plane. What other point lives on this plane? Give me something, again, let's draw something that's on the xy plane. So let's let z be 0. Give me another solution to that. X is 2, and y is 1, right? X is 2, 1, 2. Y is 1, I think somewhere around here, right? Do y'all agree? Do y'all see that? 1/2 and 1 would have worked. I'm sorry. No. 1 and 1/2 would have worked. Right? 1 and 1/2? That would have been 1 and 1/2. What I'm trying to get at is that this plane, because z is not in here, goes straight up and straight down. So it looks like, it looks like this. It's got a certain tilt to it because of this equation. In fact, if we draw this and connect these on the ground, right, that's the line that it hits the xy plane in. So I don't want to draw this plane coming up out, okay, because I think that's going to cause a problem if I try and draw it out. Imagine that this comes up through our tetrahedron. Do you see the double integral? Do y'all see it? Remember, the double integral gives us the volume underneath a surface above some region. Do you see the region in which we would want to integrate over? Do you see it in there? Okay, let me ask you something. Do you see the surface on top? I need to go get the, what do you call it? How do you say that? Defibrillator. Y'all okay? I'm asking a yes or no question. Do you see the surface? If you don't, then you need to just tell me and I'll try and show you where the surface is. Look, we have a surface on top, and on the bottom we have some domain that we're trying to go straight down in there and get that volume underneath, right? That's what we're trying to do. Okay, do you have a top surface? Okay, where? What is it?
The red triangle.
The red triangle. The plane, right? This right here. That right there creates a top surface, doesn't it? Doesn't it? And if I can just find the volume below it, then I can answer this question, but it's the thing on the bottom is what we have to look at a little more closely. So can you write this as a function of x and y? Yes. As a function of x and y, this is 2 minus x minus 2y, right? If I solve that for z. So that, to me, is going to be the upper surface. I'm going to be trying to find the volume underneath it. When I look down to the ground, though, go straight down from here, do you see the domain that I need to work with? Do y'all see it? Yes? Okay, thank you. Where is it?
The black triangle.
The black triangle?
Between the blue line and
Right in here. Just this in here. Okay? Just that. It's difficult to see this because I'm trying to draw 3 dimensions on 2-dimensional sheet. Look, if this blue wasn't here, we would have a tetrahedron that would have this plane, the xz plane as a wall, the back would be a wall, and the floor would be a wall. And that would be a tetrahedron, right? But there's one additional thing. We're coming through and we're taking that and we're saying we're slicing it right through and we're cutting through. See, it's impossible for me to really be able to show you where it cuts through, but it does cut through and it creates that tetrahedron. I don't know if that helped. Okay? Now, it all makes sense now. That helped a lot? See, that's why I have this. this, whoa, shit. Figure out where I am here. Okay, there's the plane, right? We all agree this is the plane? Well, I didn't show much here, sorry. I thought I was going to show more detail. There you go. All right, so that's it right there. Do you see where that plane came through and sliced that thing right there? That's what I was trying to show in here, is that slice through there. All right, back to business. That's why I'm asking y'all questions. That's why I appreciate answers, because I probably wouldn't have drawn that slice unless y'all showed some resistance. But when I ask and no one says anything, I'm just assuming you're getting it, I guess. I don't know. Or you don't care enough to tell me you're not. All right. Let's draw the domain on the ground, now that I've erased that beautiful picture. X and Y. I already know my surface, right? I already know f of xy was 2 minus x minus 2y. What does it look like on the ground, though? Maybe I shouldn't have erased it, huh? We had this point, it came over, but then I came through and I cut through that way, didn't I? And the region I was talking about was this one in here. Remember, this is the y-axis, this is the x-axis. So can you label at least one point that you know for sure? 0, 0 is here. And 0, 1. We all agree with that? That corresponds to this one and this one. The other point is where these two intersect each other, right? Which is where what intersect each other? This plane, where that plane hit this plane, right? That's what you need to know. Where do those hit each other? So how can you determine where those hit each other? Well, where they hit each other, they're both on the ground, right? XY plane. So when they hit each other, z is 0. So I'm first going to let z be 0. That way I'm on the ground. And I'm going to rewrite, let's see, the first equation is this. The second equation is this one with z being 0, is x plus 2y equals 2, right? If z is 0, that's what the plane is, and that's what that plane is. Two equations, two unknowns. I see a simple way of doing this, right? If this is 2y, plug it in there, or if this is x, plug that 2y. Either way. I'll just take this one, I'll replace x with 2y. So 2y plus 2y equals 2, 4y equals 2, y equals 1/2. If y is 1/2, what's x? Which implies x is 1. So that's where they hit each other, at the point 1, 1/2. So that corresponds to this point right here. 1, 1/2. And we all agree that that's my D? Yeah? Questions? What am I going to ask myself next? What kind of region is that, right? Do I want to treat that as a type 1 or a type 2? You could do either, but one of them's easier. Look, let's look at type 1. If I do type 1, then if I move from left to right, does the top and bottom curves always stay the same? Yes. If I do type 2, do they always stay the same? Here, this one is the one on the right. The one on the left will always be this line, right? But see, once I get up to here, it switches to a different curve, doesn't it? So I could do type 2, but I'd have to split it into two integrals, and I don't want to do that, so I'm going to keep it as a type 1. Yeah? So I'm going to go with type 1 on this. Type 1. I didn't do this before, but I'm going to go ahead and put my restrictions that I know. I know x is restricted between 0 and 1. Now, I didn't do this before. I'm just showing you a different sort of approach, different notation. All right? Now, what's your restriction on y? It has to be a function. This is a type 1 region. So you cannot just say between 0 and 1, because as you move this left and right, your y value is not free to go as high as you want. Well, it can't go all the way up to 1 here, can it? It's got to stay underneath that one. So we actually need to come up with those two curves. What are those two curves? So do you know what this curve is right here? And do you know what this one is? The bottom one came from this, didn't it? And you could check it, 0, 0 lives there, right? And then if I plug in 1 for x, well, hold on. Wait a minute.
Yeah, that's right.
Oh, yeah.
Yeah, x is 1. Sorry, yeah, you get... All right, I had a little panic attack there. So the bottom one comes from this equation, x equals 2y. We agree? The top one comes from what? I mean, isn't that where that plane comes in and hits the ground? Let me see if I can rotate this around. Okay. There's that picture, right? Where that plane came in and hit the ground right here. Isn't that what we're talking about? And that means it comes from the equation of the plane when z was 0. So what's the equation of the plane when z is 0? It's x plus 2y equals 2. Now this is a type 1 region. So I want to solve both of those equations for y. So this should be y is equal to -1/2 x plus 1. Solve that for y. Solve this for y. Y is equal to 1/2 x. And in terms of matching up with the formulas we're using, this one would be g sub 2 of x. This one would be g sub 1 of x. Wouldn't it? Okay, so now writing it this way, what's the lower limit of g, or y, sorry? 1/2 x, and the upper would be -1/2 x plus 1. There you go. That should be everything we need to set up the double integral. See, you can tell these kind of get a little messy with the, just the visualization of things. So double integral, 0 to 1, 1/2 x to -1/2 x plus 1. What are we integrating? Z equals 2, so 2 minus x minus 2y. That was that surface right there. And then d y dx. There we go. Dot, dot, dot. So when the final comes around and I ask you a problem like this, it will be set up the double integral. Do not evaluate. Okay, so you'll just set it up. I mean, there will be a problem. There will be at least one problem on the final where you have to evaluate the whole thing. But setting up, getting to this point is where I'll want you to get, so we can, you know, not waste time doing integration. All right, that was interesting. Example 5. Order might matter. This looks harmless enough. I love this problem. This is outstanding. So you look at that and you're like, all right, sure. You know, trying to find the volume below this surface over some region, and I just have to be able to compute that, right? And then you go, wait a minute, what's the antiderivative of sine y squared? So you go to Wolfram alpha, and you type in integrate sine y squared. And it returns to you the square root of pi over 2 times capital S of square root of 2 over pi times y plus a constant, where capital S is, by the way, the Frenzel S integral. That should look like complete nonsense to you, all right? Which it is. Basically, Mathematica, Wolfram alpha is saying, you're not doing that by hand. That's the long, ugly way of saying there's no way you're doing that by hand, all right? Take more math classes, you'll figure out this is just kind of like an error function. It's a way of measuring error. So you just go dot, dot, dot. That's it. Move on to the next problem. I can't integrate sine of y squared with respect to y because it's something I've never been able to do. Oh, by the way, you could do it with a power series. You could get an approximation. But I wonder, hold on. I bet you Wolfram alpha did it somewhere. There it is. So the program, where's the, oh, I moved it right to the place you can't see it. Here's your series expansion right here. Here's your power series expansion. So if you use power series, you can get the approximation as close as you want. And that's how they're able to get a numerical answer. So we can't, we're not going to say there's no way we can do it. We can, but it'll be an approximation. What would be better? If, right? The big if this was dx dy, now that would be easier for me to integrate, because if I was integrating with respect to x, that would all be a constant, and then the antiderivative would just be that times x, wouldn't it? I wonder if I can switch it. If these were both numbers, I could, right? If these were numbers and these were numbers, I could switch it. But they're not.
Isn't that x equals sine y squared, and then you can solve for y?
Wait, hold on. Say again. Isn't what?
Like the integrand, or what's in there?
Here?
Isn't that x equals sine y squared, and then you could solve for x?
No, that's z equals.
Oh, z.
Yeah, it's z equals that.
Okay.
So watch, check this out. Watch what we're about to do. This is what we know. Right? That's what the double integral tells us. Right? Those are restrictions on x and those are restrictions on y. I'm going to go backwards now and draw the region from that information. Okay? I know that my x's have to be between 0 and 1, don't they? But my y values are between, what? 1 is the top and x is the bottom. So 1 being the top is this, right? X being the bottom is this. Yes or no?
Okay.
Y equals x, 1. And the way this integral is trying to approach the problem is by treating this region like a what? Type. They're trying to treat it like a type 1, right? I can switch the order of integration if I change it to a type 2. The question is, can you convert this to a type 2? Yes. Because if I draw my double arrow this way instead, will I still maintain the same left bound the whole time and the same right bound the whole time? Yes? That's what I'm going to do. I'm going to take the original problem. I'm going to give up on the fact that I'm never going to be able to integrate that. I'm going to go and look at the region and say, I'm going to switch it to a type 2. And then when I go back and look at this, it'll now be dx dy, if I can make the switch. So all I'm going to have to do to make the switch is, instead of looking at top and bottom, look at left and right. So this left bound, which we said was h sub 1 of y, what is that left bound on the y value? Or sorry, on the x value? 0, right? That's fixing my x at 0. It's always 0 the whole time. This one right here, h sub 2 of y, is this equation, which, what was the equation that drew this? Y is x. It's that equation solved for x instead of y, but it's already solved for x. So this is just y. Y? And then I just need to know my restriction on my y values. It goes from 0 to 1. So I can draw the same exact region, get the same exact answer, if instead of this, I go y is between 0 and 1, and x is between what this time? 0 and this side, y. Do y'all see that? That's pretty clever, right? Switch this over, double integral, 0 to 1, 0 to 1, 0 to y, and then the same integrand, switched dx dy instead of dy dx. And this one I'm not going to dot dot because I want you to actually see it happen. Any questions on how I switch this? There's a problem. There's a couple problems on your homework. I think there's 2 problems where it says switch the order of integration. So they give you this, and they want you to switch it over. And I promise you a problem like that on the final. Promise. All right, so let's do this integration. The antiderivative of sine of y squared with respect to x is x sine of y squared, right? Evaluating this, x equals 0 to x equals y, dy. Now I'm going to go and I'm going to replace x with y. So this is going to become y sine y squared. Going to replace x with 0, and we're just going to get 0. Right? So this will become, do it up here, integral 0 to 1. What did I say it was going to be? Y sine y squared dy. Now, is that something you can integrate?
Yeah.
Yes. That y out front saves you, doesn't it? It's just a basic u sub. Basic u substitution. Take this to be u. What's derivative of this? 2y. You've got it basically. So this becomes, I'm not going to go through the integration. I'm just going to expect you can do it on your own, on this side if you need to, whatever. This becomes 1/2 negative 1/2 cosine y squared. That's your antiderivative. Shall we check it real quick to make sure it is? What's the antiderivative of cosine of something? Negative sign of that something. Then times the derivative of what's inside. What's the derivative of what's inside? 2y. So what's 2y times negative 1/2? It should be y, and then there was a negative that popped with the sign. So it works. Okay, you go do it on your own. All right, and then I'm evaluating what? Y is 0 to 1. Plug in 1. You get cosine of 1, don't you? So negative 1/2 cosine of 1. And then minus cosine of 0 is 1. So minus negative 1/2. So you're going to get negative cosine, or negative 1/2 cosine 1 plus 1/2, whatever that is. And just leave it, that's the exact answer. Outstanding. If you were going to try and figure out what cosine of 1 was on your calculator, you would be in radian mode, right? If you were in degree mode, you'd get the wrong answer. It's radians unless it's specified that it's degrees. Okay, a couple of properties of double integrals. We didn't really need this. I did kind of talk about this a little bit, but now I'll just formalize it. In that problem that we had a minute ago, where it was this one, the tetrahedron problem. Remember I asked, we want to do this type 1 or type 2? And we decided type 1 was the better approach, but that type 2 we could do it. But if we did type 2, we would have to break it into 2 pieces because the arrows this way would be different than the arrows this way, right? This right here tells you that you're allowed to do that. Split it up. So if you have some region D that you split somehow into D1 and D2, then the double integral over the entire region D is equal to the sum of the 2 integrals over each of those regions. That's not something we can just assume is true. This tells us it is. And I believe that, no, that's not the last one. So this is a major result, and it's going to be even a bigger result when we get to triple integrals. Here's what I'd like for you to try and visualize. Let's say that we have some object. I'm going to make it real simple to start off. Let's go with the rectangle. Remember when we had rectangles? Let's just say for the sake of demonstration, this was 1 and 3, and let's say this was 1 and 4. Yeah? And let's say I wanted to do some double integral of some surface over this, right? So I lay that down on the ground. I'll try and draw this a little different. Let's make this our x, our y, our z. So our rectangle would be laying on the ground like this, wouldn't it? That's our rectangle laying down. Let's say that the function on top was this function, f of x equals 1. That means that no matter what point I plug in, how high do I go up? 1. So for every point I go up 1, go up 1, go up 1. What I wind up doing is drawing this box, right? And evaluating that double integral, right? If this is 1, then evaluating that double integral gives me the volume underneath that, right? What's the volume of this box? It would be, well, how wide was it? It was 2 wide, How long was this? 3. And how tall? 1. So it's 2 times 3 times 1, which is 6. So the volume of that box is 6. Agreed? But because it was 1 unit high, isn't that also the area of this? The area of that's 6, right? So the point is this. If you're ever trying to find the area of a weird object in two-dimensional space, you can find it by doing the double integral of the region and using 1 as f of x, y. If you do that, your answer will be the area of the region you're integrating over, always. So it's not a coincidence that the volume of this being 6 matched with the area of this being 6. They will always be the same as long as the function is 1. All right? I'll show you an example. No, I don't know. No, I don't want to do it. I don't want to do it. The reason I was going to show you that the area of a circle is pi r squared. But if I do that here, it's going to require some work. It's going to be pretty ugly. Next class, when we go to polar coordinates, I'm going to prove that the area of a circle is pi r squared, and it's going to be very simple to show. So I'd rather do it in polar coordinates than in Cartesian. So just remember that, okay? You don't want that to creep up on you somewhere where you're trying to find the area of some weird region and you forget that you can do it with a double integral. All right, this is a tough problem. We have 15 minutes. I want you, let's see, how many people have books? Yeah, is there like one book per table? I want you to look at number 28 from the book. This is on page 708. I'll tell you, I'll put all the information up here. But in 15 minutes, let's see what you can do about finding the volume of this solid, okay? It's bounded by y squared plus z squared equals 4. X equals 2y. X equals 0. Z equals 0. And it's in octant 1. There is a solid that is formed by those things. I'll give you a little hint here. All of these are planes. And this is a cylinder. See, last hint, it's a double integral. 15 minutes. I just want you working on this. You're not going to turn it in, but I want you to like actively try and get at least the picture of the ground, which I'm giving away there, but it's still not going to help you because you don't have any of the values. I'll put up a blank sheet here. Give me a second. Did I see someone raise their hand? I'll be there in just a second.
Can we do anything from this mini exam with what we covered?
Can you do anything from the mini exam? You should be able to do number 1 and number 2. I wouldn't touch 3 yet.
So we can do 2? All of it?
Yeah. Yep. Yes. Yeah, you can do 1 and 2 from the new mini exam. 2 is going to be a head scratcher, though.